And we can start. Good morning, everyone. And it's my great pleasure to introduce Narasimha Chari from IIT Kanpur, who's going to speak about the Gromov width of generalized Bott-Samelson varieties.
Thank you. Thank you, Smina. And thank you also organizers for inviting me here. Today is my talk is on Gromov width, which is not algebraic or the quantity is not algebraic one, but my objects are algebraic. Okay? And also I will mostly highlight on geometry, but I use combinatorics and the representation theory as a block box. Okay? Let's start with very basic things. So you have a symplectic manifold, which means you have a smooth manifold and you have a closed, non-degenerate, closed two form on it. So if you have an example is R2n, which is a usual take the coordinates x, y, and y. I'm not sure. Hello? I don't know, but can you hear me? Okay, that's fine. So, and also if you take any smooth manifold, now you take the cotangent bundle of that also gets a symplectic structure on it. So we wanted to see what are the morphisms between the symplectic manifolds, which we take diffeomorphism between the two symplectic manifolds. Now you demand that this pullback of the symplectic form is a symplectic form on the given symplectic manifold. So we are interested in only the symplectic embeddings, which is the smooth embedding, which pullbacks to the symplectic form on M1. So if you see what is symplectic embedding, if you take n equal to 1, that means you are in R2. So symplectic embeddings are just the volume preserving embeddings. So you can ask natural questions. So if you have a two symplectic manifold, is there nice embedding kind of thing? So how do you compare with them in some sense? And also if you see symplectic embeddings are volume preserving ones, because symplectic form is a two form. Now you take the nth power of that, you get a volume form. So since symplectic embedding, the like a pullback of symplectic form is a symplectic form, so you get the volume preserving one. But if you wanted to study locally, can you differentiate two symplectic manifold? But you cannot do it because of this theorem says that if you have any point, so this is there is the neighborhood which is locally Rn with standard symplectic form. But you might have, I mean, that means every symplectic manifold is locally symplectomorphism to Rn. So there are no local invariants. Okay? So that means you have to study some other invariants. So, yeah, so let's come to here. Maybe this is Gromov's, it's a non-quizzing theorem. People also say that this is Eisenberg uncertainty principle version of mathematical version of Eisenberg uncertainty principle. It says that if you have a ball of radius r, so this is sitting inside R2n with the standard symplectic form, the restriction on Rn to the open ball. You cannot embed into a cylinder. So you see, this is the infinite cylinder. Maybe the picture is good. This infinite cylinder, and this is like a finite volume ball. So you think that you can squeeze like this and you can embed there. Okay? But what Gromov theorem says that you cannot do unless the radius of the ball is less than or equal to the radius of the cylinder. But there might there exist volume preserving ones, but not the symplectic preserving ones. I'm sorry. Yeah, is it okay? Here you see, you might get a volume preserving ones, but not the symplectic preserving ones, which means the symplectic embeddings are very rigid in some sense. So in this context, Gromov introduced how do you measure the symplectic things. So he introduced, if you have given a symplectic manifold, he defined, you take all the balls of radius. This, I mean, this is a different notion I am taking here. You can take ball of radius r, then people take the supremum of pi r square. Okay, but some reasons I am taking ball of radius root a by pi. So this is a symplectically embedded into n. Now you take the supremum of all these a's. Okay? And here we have a standard symplectic form in your ball. So, but what we know by Darboch's theorem says that this is any symplectic manifold is locally looks like Rn, which means this Gromov width is always strictly positive, unless n is a point. Actually, we'll see some properties of symplectic, Gromov width. So I'll define one general notion of a symplectic capacity of a symplectic manifold, which is that it assigns a symplectic manifold to a number, okay? So which satisfies the following properties. One is monotonicity, which means if you have a symplectic embedding of one manifold into other, then the value will be also less than or equal to that. And also conformality, which means if you scale your symplectic form, then the value also scale by that lambda. Non-triviality is like you demand that, okay, your capacity is, the ball has always positive capacity, and the cylinder always have the finite capacity. Okay? And some people also demand that normalize it. So they demand that, okay, this capacity should be pi for the ball. The capacity for the cylinder is also pi. So nice thing is that, okay, this Gromov width is a symplectic capacity. So you can see that by definition of Gromov width, this is a symplectic capacity. Not only that, this is one of the minimal capacity compared to any other symplectic capacity. So that is why it's kind of some fundamental symplectic invariant of a symplectic manifold. So in general, it is a difficult problem to compute explicitly. So there are some known cases I will explain now. So first ones are coadjuvant orbits. So which maybe I just recall it. If you have a connected compact Lie group, now you look at its Lie algebra. Okay, you can examples are SUN or Lie algebra of SUN. So you have a natural action of K on Lie algebra dual, the coadjuvant action. Now look at the coadjuvant orbit of that lambda. So this comes with a very natural symplectic form, which is called Kirillov-Constant Suryo symplectic form, which is defined as if you take two elements in your Lie algebra. Now you associate its vector field, fundamental vector fields. Now you define that symplectic form is just given by this pairing, lambda, and this makes sense because lambda is in T dual and this Lie bracket is in T. So any questions? So now just I try to move because we are starting with any lambda in T star. So somehow I wanted to connect these to the algebraic objects. So we know that every coadjuvant orbit intersect the positive Weil chamber in a single point. So that means that the coadjuvant orbits of your Lie group is just associated to one member, positive member in your Weil chamber. So that means I can consider lambda is a positive dominant. So now, as I said, so my problem is in symplectic geometry, but somehow I want to move to algebraic side. So I'll take the complex equation of your Lie group, that is becomes a reductive algebraic group. So in this example, SL and C. So now I just define this one because I will need it later. You have a Borel subgroup and maximal torus. Now you look at the stabilizer of this lambda, and now you complexify it. So this is a parabolic subgroup inside your algebraic group G. So now there is a nice thing. So this coadjuvant orbit is, I mean, you have to put some kind of condition here. We are putting the integral one. Okay, if you put the integral one, this coadjuvant orbit is nothing but a flag variety. So now, I mean, there is a full history of finding Gromov. So first one is the natural one is Grassmannians. Okay, Grassmannian is also a flag variety. So Thorsen and Tillerman and Liu independently they computed explicitly what is a Gromov of Grassmannians. And some other types. So this is, let's say, a type A or Grassmannians. Pabinek and Pabinek obtained for the type D and type B. Okay. So, but for some condition and lambda, so they assume that this lambda is regular at some conditions. Castro has given upper bound for the Gromov for any lambda. Okay, so here he is not assuming any integral or rational condition. So this upper bound is given for any lambda for the coadjuvant orbits. So another thing is that now if you look at the lower bound, so upper bound you have it in some sense for the coadjuvant orbit, but the lower bound is there only for few cases like in these types. But Fang, Littelmann, Pabinek, they computed the lower bound, but they wanted to use algebraic techniques. So they wanted to be lie inside the flag varieties. So that's why they have taken this is a rational line. Your lambda lies on a rational line. You know that the Gromov is conformality property holds. Then you can multiply with some number, then you get an integral one. So that is why you can do it for any rational element in T star. So if you combine everything, so now you have Gromov of coadjuvant orbits. In this case, if lambda is lies inside a rational line, the Gromov is given by this this pairing. Lambda alpha check and lambda alpha check is non-zero and alpha is a simple root. This you can also see a more geometric way. You look at the curve, you look at the base point of your flag variety. So now I'm assuming lambda is integral, okay, because it's we are not losing anything. You start with the base point. Now you take this root group orbit and take the closure. So this is a T stable curve, and we know that this pairing is given by lambda alpha check. Just reformulate it this one. So we have this is just the minimum of this pairing with T stable curves. Okay. And also this is very explicit because we know this lambda alpha check to compute it given a coadjuvant orbit. So we know, so by roots. So let's see what are other known examples. So the one is like kind of a flag varieties, we know explicitly. Another one is kind of a generalized Bott manifolds. So this is also because general Bott manifolds are toric manifolds. So you have a lot of combinatorics available for you and you can do it. But this is it's not known for any toric manifolds. This is a special class of toric manifolds. These are given by the towers of P1s. If you take it, this Pi, the Ni, I mean the towers of P1s is called Bott manifolds. If you take any projective space as a fiber, so then this is called generalized Bott manifolds. So other one we also reformulated because this is a purely kind of combinatorics of polytope associated to these toric varieties. But we somehow realized, okay, that number is not something else, but you can realize from your rational cause, some particular kind of rational cause on your manifold. And also some other known cases are polygon spaces, but polygon spaces, they have done only some cases by Mandini and Pavignac. But here again, if you go into the techniques of polygon spaces case, again you reduce to the case of phanotoric and blow up of them, but which is already known by Liu in the toric case. Okay, so sorry. Yeah. It's a toric one, so we demand that. So which means, and also another class is known, toric manifold associated to certain groups. So what I want to say here, the known cases are either flag varieties or kind of toric ones. So let's see. So now, as I said, I come from algebraic side. So my objects are smooth algebraic varieties. Maybe you might ask, okay, how do you get a symplectic form on it? Now you have a polarization on your, sorry. You have a polarization on your smooth projective variety. So now you have a natural embedding of X into this projective space. The projective space has a nice symplectic form, which is called Fubini-Studi form. Now you restrict with that. Okay. So since now you have a symplectic manifold, so you started with smooth projective variety, but you ended up with a symplectic manifold. Now it makes sense to ask what is a Gromov width of this object. So in my talk, I'm interested in these two objects. One is Bott-Samelson varieties, and another one is generalized Bott-Samelson varieties. But you think that, okay, this generalized Bott-Samelson varieties, the previously one were generalized but manifolds. Okay, those are toric, but these are not in general toric. I mean, mostly never toric. So let's see what are these objects. So Bott-Samelson varieties are iterated towers of P1 bundles, but manifolds are also iterated towers of P1s, but this is kind of a twisted product you get it. Let's see one examples. P1 cross P1 or just P1 is also Bott-Samelson variety. P1 cross P1 is also Bott-Samelson variety. Hitchcock surface is also Bott-Samelson variety, but in this, I have to put some condition on this number. Okay, this is like a 1. And in general, you can also realize that inductively you can define. You start with a Bott-Samelson variety. Now you take rank 2 vector bundle on it. We know which rank 2 vector bundle also we have to take. It is known. So we can realize that this is a projectivization of rank 2 vector bundle on Bott-Samelson variety. So given Bott-Samelson. So you want to see more explicitly or elementary way. So you start with your algebraic group. I assume that my group is semi-simple and simply connected. So this is T is a maximal torus of your Z. Now you look at the while group. Now this while group is generated by the simple reflections. Now you take W is a while group element. Now you write in terms of reduced expression. Now for each, this is a simple reflection associated with a simple root. For that simple root, you can associate a minimal parabolic subgroup. So we define that this is a kind of a twisted product of P1s by the powers of Borel. Okay. So maybe if you wanted to see here, this is this, let's say this is a minimal parabolic modulo B, just isomorphic to P1. If you want to see more clear way, you can also define a product like this. So each one is a P1 and some kind of twisting is happening by Borel. Okay. So this is a smooth projective variety, and not only that, so I have come in a different way, but actually this Bott-Samelson varieties are much more related to Schubert varieties, because Schubert varieties are in general not smooth. So then the de Morzier constructed desingularization of these Schubert varieties very nicely using the combinatorics of your while group element, and de Morzier and Hensen also both independently constructed. So these are good in very in many sense, which means that you can understand the geometry of Schubert varieties using these Bott-Samelson varieties. For example, proving normality of Schubert variety uses mostly Bott-Samelson varieties, because if you have a homogeneous line bundle on here, then the cohomologies are same. But the problem is that these resolutions are in some sense very big, which means they have the fibers dimensions are very high. Okay. And also they have contracts many subvarieties. Okay. That's why we wanted to look at some another class of singularizations. Okay. So which are called small resolutions. Okay, I'm not going to the technical one. Small means somehow you have to put your fibers are kind of a small dimension. Okay, so why you want to study these small resolutions of Schubert variety? Because they behave well with intersection cohomology. You have a small resolution of Schubert varieties. The intersection cohomology of the Schubert variety is same as the cohomology, natural cohomology of your small resolution. Okay. And also this, as we know, the intersection cohomology of Schubert varieties are very, very helpful in computing the Koszalowski polynomials. Okay, so in that way, we wanted to look at for another resolutions of Schubert varieties. So this is first started by Jelewinski. He constructed small resolutions of Schubert varieties inside the Grassmannians. So this is like you can also think this is for type A case. And Shankaran and Vanchinathan, they have studied small resolutions for in case of type C and type maybe orthogonal Grassmannians they have studied. So, but here, I mean, they also found it that not every Schubert variety has a small resolution. So they have given some kind of a classification of which Schubert varieties have small resolutions. So what Perrin did, so then he generalized these two constructions by Jelewinski and Shankaran Vanchinathan. So, which is called generalized Bott-Samelson varieties. So they are actually birational to Schubert varieties, but in general they are not smooth. Okay. Maybe we'll see what exactly the construction is in a minute. So what is the idea of Perrin's idea is that generalize the construction of Bott-Samelson variety. So what we did for Bott-Samelson variety, so you have taken a reduced expression in terms of simple reflection. But now, so his idea is to use not only you have to factor your W, but not in terms of simple reflections, but in terms of while group elements. Okay. But if you take each, okay, let me see like this. So here you take W is W1 and W2. Now you have to put this condition. Okay, maybe this is GW1 is the group generated by the simple roots appear in W1. And this is subgroup generated by U alpha plus or minus alpha, where alpha is a support of W1. And this one is the stabilizer of like the XW2, the stabilizer of Schubert variety XW2. And this one is the parabolic subgroup containing B and W1, the maximal parabolic subgroup. Okay. So I mean, like why I'm putting this condition is that I'll take this twisted product. So this should act on this group act on this Schubert variety. Okay. But here see that if you have a single factor, then this hat is nothing but the Schubert variety. The hat is doesn't do anything more. Okay. Because if you want that, yeah.
And can you tell what is this condition in terms of Weil group elements? Is it the same as lengths of W1 and W2 add up to length of W?
Yeah, this one?
Yeah, yeah.
This one is no, but this is kind of a condition which is because this is a stabilizer of your Schubert variety. So this is a way of giving that why this acts on here, right? So this is a condition to make sense of this product. Okay. Right. So yeah, so then you have a nice this fibration where the fiber, the base is your Schubert variety because this W1 is a single factor, and fiber is also a Schubert variety. Okay, and is as a natural action of this group. So and also this is like one side. Another side also you can have a map to your flag variety, G mod P upper W. So now we can extend this construction to any number of factors. We have two factors, okay, but we can extend this construction to any number of factors. Now here, like I'm putting the condition is good here. If you take a sequence of Weil group elements, I'm putting some condition here, which is more or less saying that okay, this group is acting on the right side. Okay, these are the conditions. The good in the sense, this is a good. Reduced means you take lengths of all these while group elements that is equivalent to the length of W. This is a reduced and good decomposition of your while group element. So similarly, we can inductively we can extend this construction to any W1 to Wm. So and also we have natural map. The base is again a Schubert variety, and the fiber is iteratively constructed generalized Bott-Samelson varieties. So this is called generalized Bott-Samelson variety. So our goal is to because as I said, I mean these are not smooth in general, but to make sense of Gromov, I want a smooth projective variety. So that is why I'm imposing the condition smoothness on this one, so which is equivalent to saying that this each XW i's are smooth. Because since it's a fibration, so I will demand that this each XW i's are smooth. That is why I just wanted to. Okay, so now see we wanted to compute the Gromov width of these objects, but let's see how we can proceed. There is two ways to compute in the literature. So one is you have to find the lower bound and you have to find the upper bound. Okay, you are lucky enough, then they will coincide. Okay? So this is what kind of techniques known. The first one is kind of a embedding methods, and the other one is using Gromovichian invariance. So we'll see embedding methods. So this is like if you want, then this comes again in terms of combinatorics. Okay, but so you want to find a nice toric degeneration of your given variety X. Okay. So once you have, then you can reduce to the case of toric manifolds. Okay. For the toric manifold case, you have a nice momentum polytope. Now you look at the simplex of size rho. If you have a simplex of size rho inside your momentum polytope, then you get Gromov width is lower bounded by this rho. Okay. So like, okay, now how do you construct toric degenerations? So now the idea is that using Newton-Okunko bodies, which are kind of a generalization of polytopes in case of toric varieties. This is a generalization to any variety or any projective variety. Okay. So these, I mean, I'm saying that these are Newton-Okunko bodies, not polytopes in general. But if you put this Newton-Okunko body is actually a lattice polytope, then you get a toric degeneration. This is a result of Anderson. Okay. So now, so what is your goal? If you wanted to find Gromov width of your object, then you have to find a nice toric degeneration, which is can be given by this Newton-Okunko body. Okay. And we have another result of Harada and Krea. Suppose you have a toric degeneration, then there exists a surjective map from your variety to the toric limit, such that the open set is mapping to a open set symplectic morphism. Now you, and also the momentum image of this open set U is contains the interior of this one. So now if you combine these two, okay, now you have a toric degeneration. Suppose you have a nice Newton-Okunko body, then you get a toric degeneration. And then using this result, so we already know by embedded method the toric case. Then you get the Gromov width is bigger than or equal to supremum of all simplex lies inside your Newton-Okunko body. And it not be integral. Yes, some random simplexes, but at least in known cases they are integral. Okay, yeah. So yeah. So now, so what is our idea? So now, in terms of in our case, we wanted to find nice Newton-Okunko bodies for the Bott-Samelson varieties. That means we want to find the toric degenerations of Bott-Samelson varieties. The literature, the toric degenerations of Bott-Samelson varieties are known by Grossberg and Karshan, and also by Persky. But the problem is that their degeneration not respects the polarizations. There you might not get the toric limit. The polytopes, they are not polytope, they are kind of a twisted cross polytope, something like that. Okay. So that is why we wanted to look at for another degeneration, which is we constructed actually. So I mean, again, so if you want to see how do you construct, you have to look at some kind of birational sequence, which means you have to find a nice open subset of your variety. Okay, so then you construct it, but turns out to be a string polytope. Okay, so this is a generalization of generalized string polytope, which is studied by Fujita, who is here. Thanks to him for this result. And we realized, but there's a slight difference. He uses different kind of evaluation, not valuation, different open subset, but we use another open subset. He uses to construct Newton-Cohen's bodies, he uses the simple roots, but we uses the positive roots, but somehow they are up to translation, they are same. So now let's back. So now you have a string polytope. Sorry, you have a polytope, then by using Anderson's result, so you get toric degeneration. And the toric limit is somehow associated to this Newton-Cohen's body. So the normal, in fact, they're not exactly this one. The normalization of toric degeneration is associated to this polytope. So, okay, so now what is our goals? Now you have to find a simplex. But where do you get, I mean, you take some simplex, maybe the size is much smaller. So you wanted to find the best approximation which can be included inside your polytope. Okay. For this, we come we cheat here. We go to upper bound, then we take that candidate and then come back, okay, this is the guy. So for that, we go to the upper bounds. Okay, for upper bound, we use Gromovian invariance. I'm not very expert in this candidate because this is very difficult to define what is a Gromovian invariance. In very nice cases, like if you have a or monotone manifolds, it is very easy to define, but in general, it is very difficult because you don't have a fundamental class of moduli of J holomorphic cos. But intuitively, what does it mean? What the Gromovian invariant means? It's count the number of J holomorphic cos with some incidence relations. Okay. So what Gromov's proved that if you have a compact symplectic manifold and given a curve class, if this Gromovian invariant is non-zero, that means there is this step car. I mean, and also you wanted to put this point is I mean, you want to insert, I mean, this car should pass through a point, at least one point. Okay. This is what this non-zeroness says. If you have certain curve, then he proves that this Gromov is upper bounded by the symplectic area of that curve. Okay. So our approach is not by J holomorphic cos. We wanted to use the algebraic technique. So we use the rational cos. So in fact, yeah, sir, X is M. Okay, because sometimes X is for algebraic, M is for symplectic. So maybe I messed up here, but yeah. So we actually wanted to use a nice class of rational cos, which has a minimal rational cos. So what are the minimal rational cos? The rational cos, which means the map, non-constant map from P1 to your variety X. Now we take the subclass of this rational cos passing through a general point. Okay. We demand that I mean, the definition of the minimal rational family is that if you take this subclass, okay, that has to be non-empty and projective. Okay. So maybe if it is too technical, maybe you can also use the minimal degree cause, okay, which means you start with your very ample line bundle, and you take the curves passing through a general point. Now you take the minimal degree of this line bundle along that curve. Okay, so this is like I'm not saying that minimal degree curves. I mean, not every minimal degree. Sorry, so minimal degree curves are minimal rational, but there might exist a minimal rational curves which are not minimal degree. So in our Gromovian invariant, so we take this curve. Okay, we take this minimal rational curve, but in fact in our there is a result which says that if you take, because we are looking at this intersection one, okay, the minimal degree of the minimal ration cause obtained for a minimal what I want to say is that if you have an intersection, you take all minimal rational cause, but that curve is going to be minimal degree. Okay, so that is why. So using this candidate A, we proved that if you have any projective complex manifold with a scalar from omega, for this minimal cause, you always get this one. Okay? This result is actually what is here, what we have to prove here. So we have to prove that using this curve, we just get this non-zeroness of Gromovian invariant. Okay? So here, this is basically in some sense, it's not a new result. It is already observed by Kolar and Ruan. Okay, if you take a minimal degree curve, so then you get such kind of thing. Okay, but it is not like a how to say, they have mentioned it, but they know the result. But that's why I would say it's not new one, but we observed somehow in a different way. Okay, so now let's now you take the minimum of all these symplectic areas over the minimal cause, and what we get it this Gromov is upper bounded by this candidate. Okay, so now I have upper bound. Now I'll go back to my lower bound. Okay, so this is my candidate to find it for lower bound. So now next is that now okay, I have a this number. So now my goal is to find simplex of size k inside your Newton-Contour body. Okay. So yes, we try to find it. Okay, but here I'm somehow this is purely combinatorial one. So you have some polytope. Now you have to find a simplex inside that. Very simple question, but it's very hard to find it. Okay. But here our idea is that representation theory ideas. Okay? If you look at the Gromov Newton-Contour bodies, it comes from the global sections of line bundles. Okay? Which means these are what? These are actually demerger modules in some sense, right? But at least I am not mentioning here, but we used a lot of representation theory ideas here. So then using our lower bound theory, so we have a polytope and a simplex. Then we go back to our lower bound theory. So that means we have a lower bound for this. Okay. So, but we already observed that okay, upper bound is also this one and the lower bound also this one. Somehow we are Gromov we are squeezing between these two bounds. So, I mean, somehow we are lucky enough to get a lower bound. Actually, when we prove, this is not the one we used in our Gromov of Bott-Samelson varieties. So this, we used actually result of Michel and Kannan. So they have given what are the minimal rational families on Bott-Samelson varieties very explicitly. We use their explicit characterization to obtain a upper bound of Gromov in case of Bott-Samelson varieties. They are given very explicit, so that's why we can make it use of them. Now also you can see here, I mean, okay, maybe you said that, okay, you have given this number. So can you compute explicitly? Yes, we can compute it because we have a line bundle, we have a nice classification of line bundles and Bott-Samelson varieties, which is given by Thompson and Lorothson. Okay. And C is thanks to Michel and Kannan. So they have given nice curves. Now you have both there. But more or less, you have to do the intersection here, but somehow you reduce to the intersection inside flag varieties or Schubert varieties. So, like you see here, this result we already known before. Like, for example, go back. Fang, Littelmann, Pabinyak given upper bound, lower bound, and Kasser given upper bound. But we can also recover this one here by our result. Because this is a T-stable cause and it's a passing through the generic point. Then we have upper bound. And the lower bound, because this we have done for Bott-Samelson varieties, which means G mod P is also a Schubert variety. Right? So then we take the resolution of that one for W equal to the longest while group element, W naught. So then we just recover this one. Okay. So, okay, let's come back to my, this is the one. So now you start with generalized Bott-Samelson varieties. As I said, we have to put the smoothness condition. This is a kind of iterated fibrations with fibers or Schubert varieties. Schubert varieties need not be smooth in general. So then you put the smoothness condition here. Then we obtain the similar result for generalized Bott-Samelson varieties. But here also we kind of cheat. We don't know what are the minimal rational costs. Okay. Michel and Kannan, they have studied for a minuscule case, but in general we don't know. But they have a nice observation that any minimal rational family has a T-stable curve. So, but we know that which are passing through a generic point, but we know that this minimum attains for minimal rational cause, then we get this one. Okay. Somehow without knowing minimal rational cause, we are able to compute it. And also these curves, again, so these curves inside generalized Bott-Samelson varieties. But again, thanks to Michel and Kannan, so they actually somehow comes to Bott-Samelson, comes from the Bott-Samelson variety. Okay. And these generalized Bott-Samelson varieties are birational. So now Newton-Okunko bodies are same. And you have T-stable curves. I mean, here I'm forgetting, but these are all T-stable curves. Okay. Then we obtain this one. Okay. But here we, I mean, if you ask me, can you compute this one? We compute it, but without knowing minimal rational cause, because we know we work with only the T-stable cause. Okay. And also we kind of characterize line bundles and generalized Bott-Samelson varieties also. But again, this everything theory will boils down to the case of Bott-Samelson varieties. And Yogendra Singh is my student, is somewhere there. So we did this one. Yeah, okay. So there is some nice, I think I have some 6 minutes. So there is a nice applications of Gromov and that related to Sheshadri constant. Suppose you have a smooth projective variety and you have a NEF line bundle. NEF in the sense intersection with curves is kind of a positiveness or non-negativeness. So Dimali defined the notion of Sheshadri constants. So you take infimum of this ratio and the intersection number with C and the multiplicity of the point on the curve. Now you take the infimum over all irreducible cost. Okay. Why Dimali wants to name this one as a Sheshadri constant? Because of the following result. So Sheshadri given a ampleness criteria. Okay. So he proved that if L is ample, if and only if this quantity is positive for every point. So again, by result of Brion and Ciliabeg, we proved that this Gromov width is upper bounded by, which one is the Seshadri constant is upper bounded by Gromov width. Okay. Somehow we get it. We can also relate, just state it. The Seshadri constant of a line bundle here, but here we have to use L is very ample. Okay. So now we have upper bound for Seshadri constant at any point, but I believe that this is going to be equal at least for general points. I expect that this is equality is true. I mean, and also another thing, so the Seshadri constant for the flag varieties is not known, but from our result, we can get it because it's kind of homogeneous. And also there is a relation between the Newton-Okonkwo bodies and the Seshadri constant. It is a result of Ito. We observed that okay, Seshadri constant can be estimated from the Newton-Okonkwo bodies. So then we can, in some sense, we have a Seshadri constant for the flag varieties, which is we believe that it is not known before. Okay, maybe I'll.
Thank you. Questions, comments, remarks? I think that I have one. Is this story, well, does it give something, anything about Kazdan-Lustig polynomials?
This one?
Yeah, well, is Gromov with somehow related?
I don't know.
Okay.
Kazdan-Lustig polynomial or yeah, maybe the objects will give generalized Bott-Samelson varieties might give. Because we are looking for small resolutions, right?
Yes.
But this Gromov width, I have no idea.
Okay.
Yeah, I have a loose question because you have so many birational morphisms.
Yeah.
How does the Gromov width behave under birational morphism?
Yeah, you
can somehow control minimal rational curves.
Yes.
Push down, but
see, you might, I mean, I said the Newton-Okonkwo bodies are same. Yes. You might have the lower bound, but I have no idea from how do you come from upper side.
Okay.
So
you have only some.
Yeah, some estimation I have it, but upper bound we have no idea. Because for upper bound the techniques only we use this Gromov-Witten invariance, non-zeroness. For that we use minimal rational cost. So, but we don't know how. Maybe you should tell us how it behaves, the minimal rational cost in a birational way. So, okay. Thank you. Yes. Actually, width. You mean width? Yes, actually that is true, and it was a conjecture of someone. We proved. I mean, okay, that is not related to this one, but for the toric manifolds, we proved that conjecture. So they said that okay, you take this is a width of your lattice polytope. Actually, that gives the lower bound or upper bound. Yeah, it is related. Yeah. Yeah, but in case of toric varieties, we know, but no, see, the idea is that you have to find a nice simplex inside that. So I don't think this lattice width will help in case of Grassmannians. But in case of toric ones, we have proved they made it as a conjecture in the toric case, but we observed it. It is true. Yeah, in fact, you don't have to find simplex. You can. These are called cross polytopes. I mean, these are not polytopes. So the cross polytopes also helps. But so far, what we know, the results are for the simplex is you are getting the nice one, the simplex you are getting. But it is related to lattice width.
Yes. If not, let's thank the speaker again. And we resume at 11.